Hello, my name is Paul Fanning and I'm editor of Eureka magazine, and I'd like to welcome you to today's Design Online webinar in association with Keyence UK, and entitled Improve Test and Development Through 3D Microscopy. This will be presented by Keyence's Senior Applications Engineer, Microscope Division, Claire Lillywhite. But before I hand over to Claire, I'd just like to remind you that you can ask questions during the presentation by typing them into the box on the right-hand side of your screen. We'll hopefully have time to answer these at the end of the presentation, but should we not, we will be passing these on to Keyence, and they will hopefully be able to answer them for you offline. And with that, it just remains for me to hand over to Claire. Claire.
Perfect. Thank you very much, Paul. Hi, everyone. As Paul said, my name is Claire Lillywhite. I'm the Senior Applications Engineer for the Microscopy Division at Keyence UK. Thank you very much for taking the time to join our webinar today. Hopefully you'll find it useful and interesting. So today I'm going to talk about applications of 3D microscopy in a variety of different industries. I'll also talk about some of the common challenges faced by these industries and explain how 3D microscopy can overcome these challenges. Also, some of the benefits that new technology has over older, more conventional microscopes. So, before we dive into the core of today's webinar, I thought I would quickly introduce Keyence, just for anyone who's not so familiar with our history or maybe some of our technology. First of all, we were founded in 1974. We're actually now the second largest Japanese company by market capitalization, just behind Toyota. We're also considered to be one of the world's most innovative companies, with Forbes ranking us in the top 100 for 8 consecutive years. At Keyence, 70% of our products are industry-leading or world's first technology, including our digital microscope, which this year received an R&D 100 award for innovation. Keyence now has over 8,000 employees globally. We cover 46 countries, so there's always going to be an engineer nearby ready to help if you need anything. On to talking about some of our products. We provide various factory automation equipment, including things like sensors, vision systems, code readers, safety systems, inline and offline measurement systems, laser markers, and microscopes. Okay, we're going to go on to the main contents of my webinar today. So as you may be aware, 3D microscopy is quite a broad topic, and it does have several benefits over sort of more traditional systems. But just to keep the length of the webinar to a reasonable time, I'm going to focus on 5 main areas. These areas are depth of field and flexibility, 3D composition and modelling, 3D stitching, 3D measurement, and finally a world's first technology called Optical shadow effect mode. I'm going to go through each of these techniques in turn and also demonstrate some of them on my VHX 7000 here beside me. So the first benefit we're going to look at is flexibility and focus. Now, most traditional styles of microscope have a fixed frame and small objectives that would view the sample from above, directly top down onto the sample. This style of microscope is very traditional, but it does have several limitations. The first of these limitations is the range of angles that the surface or the subject can be viewed from. So, for example, on the left-hand side here, you can see this PCB, but you can only see the tops of the components and the flat surface of the PCB itself. With these microscopes, you typically have to manipulate your part by hand underneath the lens or fix it in place in order to view different sides of the components. If you then decide to look at the sample from an angle, you run into a related problem, which is focus. And this can be seen in the image on the right-hand side, where you've got a thin band of focus just on the lead from that component. So I'm going to show you how this works on the VHX. If I move to our microscope here. We've got a gold cutting tool on the sample. And you can see, gold cutting tool on the stage even. As you can see, our microscope is a little bit different from the traditional systems that I was just describing, because there's no eyepiece. Usually you'd have something like a binocular or a single eyepiece that you'd look through. We've actually got a camera. So we've got this camera, which is a high performance camera. We also have something called our FI head, which is a fully integrated head, which I may come on to later. This does make our system really flexible. In fact, it's possible, if I just unlock it here, to tilt the camera. So we get our top-down view, but we also can tilt it up to 90 degrees. So we can view the sample from any angle that we want to. We can tilt and rotate to see the sample wherever we want to. We don't have to touch the part. We can just place it on the stage and pop it there. Now, as I was saying before, if you view the sample from an angle, and then maybe also zoom in, let's do it right now, you typically only see this small strip of focus. So I'm going to zoom in here now so that we can see the centre of this cutting tool. And here we can see that single band of focus I was talking about. As I move the focus up and down, the band of focus moves. This is not very helpful when we just want to see the whole thing. So what we can do with the VHX is use something called live depth up. It's just one button on our console. I press it once, the camera moves upwards and stacks lots of images on top of each other. In this case, it's quite a large area to cover, so I'm just going to up the live depth up to our medium. So here we end up with the full sample in focus. So we can really see those hairs and the defects inside the cutting tool there. It's not particularly nice, but it's quite useful. So just to go back and show you, I'm just going to show you a couple of images that sort of highlight how this is useful as well. First image is our bug. Now with a traditional microscope, you'd have this on the stage and you'd just be looking top down. You would get none of this sort of more photographic view of the bug itself. With the tilting and the manoeuvring of the stage, you can really see the colour and the shine on the bug's shell, as well as being able to get a good look at its face and its eyes. Here we've got something maybe a bit more boring, but very, very useful nonetheless, is solder joints on a PCB. We can, by tilting and then doing that live depth up function, we can get the full thing in focus, so we can really analyse the join on that solder. Here we've got a mould, a die mould. We've got the hole at the bottom there, which we can measure top down in 2D view. But if we want to see, as you can see at the bottom right hand corner, we want to see inside that hole to see if there's any debris or defects, we just tilt the microscope, perform the live depth up, and we've got a fully focused image to be able to see all that we need to see. The last one on this is just this crocodile clip. Maybe we just want to pop it on the stage and not touch it, but we still need to be able to see into each of the teeth that we've got in the crocodile clip. Here we've just tilted it, adjusted the lighting so that we can see exactly what we need to see in those teeth. Okay, so that's our flexibility and focus. Next, let's have a look at actually doing a 3D composition. Because at times it's important to understand the actual shape or the surface topography of a part. For example, there might be a raised bump or a dent in the surface. We want to actually know which one of those it is. Sometimes it can be very, very difficult to tell if it's just a black spot. It could be raised or it could be indented into the surface. With 3D microscopy, we can easily get that information about the relief of the surface and give a more detailed understanding of the 3D shape. For example, here we've got 2D view of the tip of a needle. Here we get very little information other than the colour of the sample, maybe some surface texture, but it is quite difficult with just a 2D image. So now I'm going to show you how we do this on our VHX. I'm going to go back to our cutting tool. If I just move over here, you might be able to see coming into focus an M and an R. I'm just going to go into a slightly higher magnification to show you this even closer. Now, at this magnification, we can't actually really tell whether this is engraved in the surface or whether it's raised out. So what I'm going to do is build a 3D model just with 2 clicks on my console here. We use our depth composition in 3D. Press it once, it takes us into the correct menu. Press it twice, we start building our 3D. Press it again and it stops. Now how we do this, as I sort of touched on before, we stack those layers of in-focus bands together. Do you remember the band of focus that we had on the inside of the cutting tool? We basically take those and we stack those together and track the height value of each pixel as it comes into focus. So here now we have our fully focused 2D image. We can then quite easily switch to 3D just by pressing our button again. And here we can see our 3D model. Doesn't look like 3D, but as soon as I grab the corner and rotate it, you'll be able to see that the M and the R are definitely engraved in the surface. We can switch between then just this normal 3D model with the true colour. We can add a height colour map very easily, just to show the lowered sections of the blue and the higher sections of the red with everything else in between. And then we can also add a scale if we want to get an idea of the measurements on the part. So here you can really clearly see, hopefully, that using this 3D model we can get a much clearer understanding of the part and its condition, and if there are any defects or anything like that on it. Just to go into a couple more examples of how this can be used, I've got some more images. So first of all, we were just seeing the 2D image of the needle. Here we've got a full 3D rendering of the tip of the needle. So we can now really clearly see the surface texture on the inside of the needle, as well as the actual shape of the top of the curve of the needle. Here, not quite as interesting, this is concrete. You can see the pits where the blue sections are and the raised sections where the red is, just to get the overall surface texture of the concrete. Here we've got a printed section. There's a grid printed onto plastic or paper, and you can really see very clearly where the raised sections are, where it's been printed onto the surface, and the lowered sections there in the blue. Finally, we've got a comparison image. This is actually some rubber. So on the left-hand side, we've got one that is fairly smooth, but with a deep valley down the middle. And you can really clearly see that with the red raised section and the blue and yellow going down the middle. And then on the right-hand side, we've got a much more bumpy surface, just very uneven over the whole thing, hence the spattering of red and yellow and green and everything on there. Okay, so that's general 3D composition. That gives us a 3D in one field of view. But sometimes we might want to zoom into a higher magnification, get a bit more detail. But the problem with that is that the more you magnify, the smaller your field of view becomes, and so the less of the sample you can actually see under the microscope. For example, here we've got a single field of view of a diamond cutting tool. You can see some of the diamonds embedded in the surface there, but maybe we want to see the overall wear and tear of the part. Maybe we want to be looking at the entire surface to be able to see whether it needs changing or not. So what can we do? Well, we can employ something called 3D stitching, and I'm going to show you how this works on our microscope. So I'll switch back. Now I've got something else on the stage here to show you. If I just zoom out, be able to navigate to it properly. Here we go. It's just a PCB with a ball grid array on it. Now, this is fine. I can get an overall image, but I want to get much more detailed and look at exactly the shape and the size of the balls on this array. Now, as I zoom in, I'm going to lose focus, naturally. All I need to do is just get close enough to the focal plane that I can see what I need to see. And then we're going to build up a 3D stitch. All I need to do is press the image stitch button on the console. That takes us to our menu. We've got the option to choose between either 2D or 3D image stitching. We're going to go for 3D, obviously. Now I've already set up our area here. All I need to do is click Next, set our upper and lower limits for that image stacking, just so we know, so that the system knows exactly where we want to be stitching, and I just press Start. So what we end up with after this will be each individual stitch will have as much information as the one next to it, so we end up with a really high resolution image of the entire section of the part that we want to look at. So what it's doing is matching one image to the next to be able to see exactly where those stitches should meet and align properly, so we don't get any stitching lines between them, and we get the full 3D effect of the ball grid array. That's just processing. So now we've ended up with our fully focused 2D image with all that lovely information on it. We can go to our 3D menu, and here we go. We've got our ball grid array in 3D. And again, like before, I can add my height colour map so that we can see where the raised sections and the lowered sections are. We can also add a scale to get an idea of the height of those of the balls on the PCB. Some more examples of where this 3D stitching can be used. I've got some images here. First of all, we've got our cutting tool that I showed you a second ago. Here we've done a full 3D composition of the whole thing. So we can see both all the surface of the part, but also the height of the cutting tool off the surface of the stage as well. Secondly, we've got those 3 pins, connector pins, from a connector pin like you have in a computer. Usually you'd only be able to see maybe one of those in each field of view. We've done 3 by doing the 3D stitch across. This one is a component again on a PCB. Again, you'd be able to see very, very little of this component without stitching. What we've done is stitch the whole thing so that we can rotate it, be able to see all of those leads on all 4 sides of the component really clearly. And finally, we've got some kind of drilling tool that we've looked at to be able to see in full 3D. We've got the full stitch of every side of it. Right, so that's 3D stitching. And it's all well and good. These 3D models give us a really good idea of the shape of the sample. They give us an image of the sample. But if we want to, we can take it one step further and actually perform 3D measurement. Because with something like this, we've got this 2D image, but we have no idea how tall these pins are coming out of the image. We can probably tell just by looking at the image that they are raised up out of the surface. But yeah, what if we want to know the exact height? Because measuring these small samples can be really difficult. That or very time consuming with sort of typical measurement systems like a CMM or a laser profiler, perhaps an interferometer. Each of those has its own challenges, but I'll show you how we can do it on VHX. We're going to use the stitch that I've just done on this ball grid array. All we need to do is go to our profile measurement on the side here, and I'm just going to draw a line through the balls here. That's going to create us a profile on the bottom. They look a bit strange shaped, so I'm just going to change the graph down here. There we go, much more realistic. So now we've got then an array of different 3D measurements to perform. I'm just going to keep it simple and use our max min tool here, because what this is going to do, I'm going to click and drag over one of these balls. It's going to show me exactly where the top of the ball is and also where the lowest part on the PCB is. And there we go, we've got our measurement. I can keep doing this for any and all of these balls. We can actually do up to 99 measurements on each profile, and they're really quick and easy to do. You get your profile measurement like that. We can also do volume measurements and also to some degree roughness measurements as well. Again, just a few more images to show you exactly how this can be helpful to you. Here we've got one of the balls that we've looked at, so really nice high resolution image of one of them just to see exactly how high that is raised off the PCB. The second one is actually an indent into some plastic material. We can see there's a large defect on the right hand side of the profile there has been measured, but we've actually performed 6 different measurements on this profile, but really, really quick and easy to do that. Here we've got, similar to what we saw before, we've got a stitch all the way down the edge of one of the PCB components, and we can see exactly how high each of those legs are off the PCB. Really easy to draw some parallel lines going across the bottom and the top of those and measure between them. And then something a little bit different on the last image, we've got a cross-sectional area of the solder underneath a lead on a PCB. Yeah, just something a little bit different that we can also do on the VHX is this surface area, this area measurement. Okay, so that's 3D measurement. Finally, we actually have a world's first feature to share with you, and that is our optical shadow effect mode. Now, some samples have features that are really difficult to see with a conventional system, or they might take a lot of fiddling around with the lighting to observe them properly. Take, for example, this image here. We've got the standard lighting image, which is just the blue and gold PCB. Now, when you look at that with a glance, you wouldn't be able to maybe tell that there are defects on there. There is maybe some slight discoloration on the gold there, but it's very difficult to tell without any kind of manipulation of the sample, any kind of changes that we make to the image. We then go to the optical shadow effect mode image, and we've got exactly what we need. We've got those bumps on each of those gold pads, and they just really stand out. Now, to show you a bit more about maybe some other applications that this might be useful for, I'm just going to move straight onto the images. Here, though, we've got a PCB again. We've got these gold pads. Really, really easily, with applying the optical shadow effect mode, we get an image that almost looks like what you might get out of a scanning electron microscope. But what we can do is actually add the colour back into the image, so then we end up with what we've got on the left-hand side there. So you can really see both the texture and the colour. So this is exactly what I was just talking about. We've got the colour added back onto the CPU there. We can really see the dents on each of the gold pads, as well as the true colour. Here we've got a transparent sample, so a plastic sample that's very, very difficult to see any kind of features on there with normal lighting. That's the image on the left-hand side. On the right-hand side, we've applied our optical shadow effect mode, which literally takes 3 seconds. We press the button and it's done. And here we go, we get our monochrome image for the shadow effect mode. However, we can also apply something called the texture color map, like what we've seen with the depth composition, to get something like this, where it's really, really easy to see the red sections are the raised sections and the blue sections are the lower sections relative to what's around it. So that's our optical shadow effect mode. That's the world's first feature. We just have one more thing to cover just before we start answering some questions. I actually just wanted to quickly introduce our 3D microscope range. So just go back to the correct page. So here we go. On the bottom of the screen, we've got our VHX 970F system, and this is our standard base model. It's capable of both 3D imaging and 3D measurement. The middle one is our VHX 7000 with the high performance camera. This is what I've been using today. This is a really highly capable system that's fully flexible, as you've seen earlier, and we can actually also support handheld use. You can take this off and use it in your hand. The top image that you see on your screen now is our VHX 7000 again, but this time with the fully integrated head. This is also a 3D system that is capable of 4K imaging. It also incorporates seamless magnification changing from 20 times all the way up to 6,000 times magnification, with a motorized revolver head to switch between those lenses. Right, I think that about brings us to the end of the main content for the webinar. I'm going to hand back to Paul, and he's going to ask me some questions in our Q&A section.
Good afternoon, everyone. As you may have guessed, the presentation you just saw was pre-recorded. So thank you very much to Paul, who was my compere at the time of recording. Thank you very much to Engineering Design Show for having us this afternoon. My name is Claire Lillywhite, as I mentioned earlier. But we've had some questions come in. I'm hoping we can see those questions soon. So what's the current lead time like? Is it readily available? This is a common question because, as we know, as a result of COVID, Brexit, etc., there have been some supply chain issues. That's not the case with Keyence. I'm happy to report we have plenty of stock in the UK ready for immediate shipping. So any stock that isn't readily available in the UK will be shipped over from Japan, and the maximum lead time that we would have on that is 10 days. So yeah, if you have any requirements at all, please do just get in touch. We had another question. Please, can you discuss pricing? Yes, absolutely. So as the VHX is a modular system, there's actually quite a few different options to run through. I've actually got a brochure here that I can show. So as you will have seen during the webinar, we have the 3 sort of main options, including the 7000 with the FI head or the high performance camera, or we've got the 970F, but we actually have quite a few more options in terms of the stands that we can offer. We've obviously got the different controllers, but the lenses as well, quite a few options. And so that means that the price of the VHX can really range quite a bit from the from the lower ends of maybe about £20,000 up to 80,000, even greater if you really want to have every single option that we offer. But as I say, it's very modular. So even if you buy a system now, we're always very good at making sure that anything is compatible. So you can add and swap in and out things as you need to. Okie dokie. I think that's about it. I don't think we've had any others. If you can just get confirmation from the EDS team. No more questions. Perfect. Well, thank you all very much for joining. As it said in the webinar, the pre-record earlier, if you just get in contact with us on webinar@keyence.co.uk if there are any further questions, or give us a call on 01908 696 900, and you can speak to your local sales engineer who'd be more than happy to help. Thank you very much. Have a wonderful afternoon.